In Lecture 8, we're going to explore how myoglobin and hemoglobin are involved in physiology. But before we get to that, we need to understand a few things about ligand binding. And ligand is a term we use in biochemistry. It might mean something a little bit different from folks who have studied inorganic chemistry. Ligand really just means something that's binding to an enzyme or a protein. And so we say ligand binds to a site, just like, as we'll see later on, a substrate binds to a protein or an enzyme. So we'll kind of use both those terms. Let's think about what we're going to call the single site or the simple case, the simple ligand binding situation where a protein and its ligand can interact. And we're going to show this as a dissociation. So sort of generally speaking, we have a protein that is interacting with a ligand X. And so this dot here indicates that they are interacting. Well, that X group can unbind via a process that's in equilibrium to yield free protein and free ligand. And so this is a dissociation event, and it's an equilibrium process. We've got what we could sort of consider products on the right-hand side and reactants on the left-hand side. And so we can write a dissociation expression this way, where we have Kd, a dissociation constant, is given by essentially products over reactants. So the concentration of free protein times the concentration of free ligand divided by the concentration of the complex of the protein ligand that are bound together. And we're not going to go through this little derivation, but we could rearrange some things, and we'll end up with this new idea called occupancy, or capital Y, equals the free ligand concentration divided by the sum of Kd and that free ligand concentration. This Y now, this capital Y, is what we call the fractional occupancy. It's essentially the proportion or the percentage of proteins in a population that have a ligand bound to them. And so you can see that in the definition down here, where you've got how many or what concentration of protein ligand pair is there divided by the total concentration of protein, right? So in this case, total concentration of protein is free protein plus the protein bound to that ligand. Those are the only two forms that are present in solution. So the fractional occupancy, right, is we could express it as a decimal or as a percentage, but it's the proportion of proteins that have a ligand bound to them. So let's look at a plot of these values where we're going to look at this fractional occupancy. We're going to look at it as a function of the ligand concentration, X. This is going to yield a hyperbolic curve, and it's going to saturate at high ligand concentration. And so it's going to look like this. We're going to see a curve like this a lot in this class. And it should make sense that at low ligand concentrations, we're not going to have a lot of proteins that have a ligand bound to them. In fact, at 0, it should be 0. But at really high concentration, we're going to get to this point where we've bound up all of the protein sites, and there's no more sites to bind, and so we can keep increasing the concentration of ligand. It's not going to matter. And in between, we have this curve. Well, let's be a little more explicit about what some of these values are. So if we go over to where that plot maxes out, we call that 1.0, or we could also call that 100%. I'm going to find where that 50% value or the 0.5 value is, and I'm going to take a line over to the plot and drop it down to the x-axis, and we're going to think about that point right there. It turns out that this is numerically the Kd value for this, and it has the same units as X. So we measured X in concentration here. Kd has the exact same units. So if this is molar or millimolar, Kd will have the same units there. Now, for those of you who remember, equilibrium constants don't technically have units. That is true, but we're defining Kd a little differently, and it very much has units. Kd will have units of concentration. So Kd is both this expression we saw on the previous page and this ligand concentration that gives us 50% occupancy. And so it's a property then of the ligand and protein pair. So it tells us how well these two things interact. If KD is a very high number, a large number, that tells us that there's low affinity between the protein and its ligand. But if KD is a low number, it actually, there's high affinity. And so just to give you a quick idea about this, consider two curves on the same plot. One of them looks like this, and the other one looks like that. Now notice they both get to this top value of 100%, but it takes much lower concentration here, right? This has a low KD, but this one has a high KD. If you want to kind of identify where the 50% mark is, you can sort of mark where those KD values would end up intersecting. So this curve represents a protein ligand pair that has very high affinity, and this represents a protein ligand pair that has considerably lower affinity. And it actually kind of is analogous to Ka. Remember that in Ka, describing the acid dissociation equilibrium, that's kind of the same idea as it was for Ka. Because if you think about it, if we had some group interacting with a proton instead of a ligand now, this is kind of like an acid, a very stronger acid, and that means it's going to lose that proton. And so you can see how there's a bit of a similarity or analogy between them. Now I want to spend a few minutes understanding the difference between, right, so affinity versus saturation. So affinity is essentially a value of KD. KD tells us the affinity, how tightly that pair interacts. Saturation, however, this depends on the concentration of X. And so what we're really asking then for questions about saturation is, where are we on this y-axis at different concentrations of X? Where are we along this curve? What I basically did for this is we went back to this equation right here, and we can plug in values for the KD and for the ligand concentration, and we can explore how saturated the protein is at those different concentrations. So for example, a KD that's 1 micromolar, and we have a ligand concentration that's 10 nanomolar, so quite a bit smaller than the KD value. That means that on this plot here, we're somewhere down here, right? We have a very low saturation. And so as a result, we're going to have only 1% of sites will be occupied, so low saturation. You can plug these numbers into the equation and you'll see that. Now if the ligand concentration is 1 micromolar, well, that's equal to the KD, and by definition, that is the 50%. That's what KD is. And now if the ligand concentration exceeds by quite a bit the KD value, well, now on this plot we're somewhere out over here, right? We are where it has become saturated, and we then expect that a lot of the binding sites will be occupied, and in fact it's 99% in this case. We can kind of flip it around. Let's say we're going to hold the ligand concentration steady at 1 micromolar, and we're going to explore maybe different proteins in a solution that have different affinities for that particular ligand. If we have a situation where the KD is significantly lower than that ligand concentration, well, now we're going to have a highly saturated event. If they're equal, it's going to be 50%. And if the KD is much higher than that ligand concentration, now this one is going to be 1%. You can plug all those values in, and you'll see you'll get the same answers. So hopefully that demonstrates the difference between affinity, which is how well a protein and its ligand interact, and that's reflected in KD, how that varies from saturation. Where saturation, we're taking into account both the KD and a ligand concentration to determine how actually saturated the protein is going to be. And it should make sense that if there's a ligand that's in low abundance, that it's going to require very tight binding for that to be biologically effective.